All right, so good morning, everybody. This is January the 24th, and a couple of announcements here at the beginning. First of all, and I did send a remind message out to everybody about this, but I was able to contact WebAssign yesterday and get the grace period on WebAssign extended through January the 31st. So at the end of the day, January 31st is when it expires. So you still have time to, if you haven't registered for WebAssign, to get on and register for WebAssign. You don't have to pay until the 31st. And then, your first assignments are due January the 30th. So that'll take you through the first assignments as far as this class goes. Let's see. You do need to, if you haven't paid by January 31st, then what happens is you just no longer have access to your class in WebAssign. Your account is still, you can still get into your account and everything. You just can't get into the class. And then when you do pay, then you just get access back to the class. Anything that you've done before that gets saved, so it's not like it throws everything out or anything like that. So if you're still having some issues, please give me a call or an email or something. I've also been in touch with the people at school and the bookstore yesterday about making sure that there's some WebAssign codes in the bookstore as well. So hopefully that's getting worked on and everything should be okay over the next few days. So let me remind you that I do have online office hours. I'm going to continue to remind you of this every lecture to remind you that I will be online Tuesdays and Sundays in the evening, and then Tuesdays, Wednesdays, and Thursdays in the late mornings. And please don't hesitate to stop by if you have a quick question. Cynthia, who's with us today, this morning, watching this lecture live, she was working on her homework last night and ran into a question. It happened to be the time during when my office hours were. She just logged on, got her question answered, and it was done. And it offers you a great opportunity to get in touch with me and get a question or two answered quickly. And so please don't hesitate to use those online office hours. Also remember that if those hours don't work for you, I can usually make an appointment to meet with you in the WebEx classroom at a mutually agreeable time, so outside of those hours. So if those hours don't work for you, get in touch with me by email or by remind, and we'll try to work out a different time. All right, so today our goal is we're kind of going off the textbook just for one section here. I do have some homework for you that's part of this lecture. There is no WebAssign homework on this particular material that we're covering. So this next material we're covering today is part of the curriculum in this course, but it's not. There's nothing in our textbook that actually covers this particular topic. And so I'm going to do this kind of outside of the textbook altogether. We are looking at our main goal is quadratic inequalities and rational inequalities. So we're turning our attention to inequalities a little bit. And so that's our main goal for the day, is to look at quadratic inequalities and rational inequalities and talk about solving those. And we'll try to relate them to graphs also as we go through the semester, or go through the lecture. To deal with that, we do need to kind of go back and review a little bit about linear inequalities and solving linear inequalities and do some reviewing there before I actually get off into quadratic and rational inequalities. So let's first deal with that. So linear inequalities. We want to look at that for just a few minutes, do some reviewing of some things here. And so first of all, remember that an inequality, as opposed to an equation, is a statement that contains an order symbol. And these are the order symbols that we use in algebra typically. We use less than or equal to, greater than or equal to. And these are called order symbols, because they put things in order. They tell you which one is on the left and which one's on the right on a number line, if you want to think about it that way. And so a typical linear inequality in one variable might look something like this. 2x plus 3 times 5x minus 1 is greater than or equal to 20, let's say. very similar to an equation, except instead of an equal sign, there's that greater than or equal to symbol there. All right, and so you solve this exactly like you would a linear equation. And so you're going to get rid of the grouping symbols, collect like terms, solve for x. So that should not be a big deal. So you have 2x plus 15x minus 3 greater than or equal to 20. Collect like terms, 17x minus 3 is greater than or equal to 20. Add 3 to both sides of the equation, you get 17x greater than or equal to 23. And then you finally divide by 17, and you get x greater than or equal to 23/17. Now, on a number line, I want to review some stuff about number lines because we're going to need to deal with number lines today also, and then also writing things in interval notation. I want to make sure that everybody who's online with me today live, make sure that when you log in live that you mute yourself and that you unmute yourself when you've got a question. So I think maybe 1 or 2 of you have not muted yourself, and so make sure that you do that. There you go, Alfonso. Thank you very much. And that way, when you have a question, it'll be real routine. Just to unmute yourself, ask the question, go from there. Now, okay, so we got x greater than or equal to 23/17. Oh my gosh, I get all sorts of crazy places where 23/17 is put on a number line. Really crazy stuff. And so here's 0 right here. So where is 23/17? Oh man, that's interesting. Remember that 23/17 is a mixed number, is simply 1 and 6/17. So 1 and 6/17 is like just a little bit less than 1.5, so 23/17 is sitting right about in here maybe, is an estimate, right? Right, this is 1 and this is 2 right here. And then we've got x greater than or equal to 23/17. So on a number line, you're talking about shading all of these values on the number line, right? You're saying that all of those x values that I've just shaded, every one of those is a solution to that inequality. So the solutions to this particular linear inequality are every real number greater than or equal to 23/17. So I want you to be able to write this as an inequality on a number line and then finally in interval notation. Now, we talked about interval notation last semester in intermediate algebra, and if you took intermediate algebra at North Harris, you should have talked about interval notation, but let's kind of go back over that again. Remember, with interval notation, what you do is you're looking at the solution on a number line as an interval where it has a left edge and a right edge, and you're writing down the left edge and the right edge of the interval. So on this particular problem, it's really not an interval, right? It's got a left edge, but there is no right edge. The right edge goes on forever. The number line or the shaded part goes off to the right forever. So what you do is you write down the left edge, 23/17. 23/17 is part of the set. Notice I put a closed dot right there, right? That's closed right there, and it's closed because this says greater than or equal to. And since it says equal to there, that means that 23/17 is actually part of the set. And so we put a closed circle there. And then on the interval notation, when you have a closed circle there, you use a bracket. All right, bracket means that value is included. And then there is no right edge to this set, right? On a number line, that it extends infinitely far to the right. And so the way we use an infinity symbol to denote that, put an infinity symbol like that. Infinity symbols always have parentheses because a bracket implies that the set stops somewhere. This set doesn't stop anywhere, it goes on forever. So you always put an infinity, enclose infinity with a parenthesis like that. Always, always, always. Also remember that on a number line, infinity is always going off to the right, and negative infinity is always going off to the left like that. In interval notation, you always put a negative infinity symbol on the left part of the interval notation of the interval, and a positive infinity always goes on the right side like that. All right, so a couple of things to point out on that inequality. And again, that should be, I think, for all of you guys, your college algebra students, that should be, everything in that process should be pretty routine. I'm assuming that there's not much issue there at all. Now, a couple of other things to talk about here with inequalities and linear inequalities. Next problem. Let's say we have negative 5x plus 3 is greater than 18. Okay, something pretty simple, but this illustrates a couple things I want to talk about. So the first thing I'm going to do is I'm going to subtract 3 from both sides. So you get negative 5x is greater than 15. And then the next thing, our next step is to divide both sides by negative 5. And so this is what I want to talk about in this problem. Remember that when you divide or multiply an inequality by a negative on both sides, right? For an inequalities, when you multiply or divide by a negative on both sides, you must reverse the order symbol, right? That's the big deal. Reverse the order symbol. And hopefully, if you've done this recently, you remember that. If it's been a while since you've dealt with inequalities, then you may have forgotten that. But that's important for us. So we're dividing both sides by negative 5 here on this inequality. And so we have to reverse the order symbol, right? So it goes from greater than to less than. And so you get x less than negative 3. And so on in a number line here, you've got here's 0, and you have negative 1, negative 2, negative 3, negative 4, and so on like that. We're talking about everything less than negative 3. So notice there's no less than or equal to, it's just less than. So we put an open circle, right, around the negative 3. That means that negative 3 is really not part of the set. And then we shade everything to the left in this case, right, like this. And on our number line, that's what the solution set looks like. And then in interval notation, the left edge of this interval, that goes on forever to the left, right? And that extends infinitely far that direction. So we put negative infinity on the left side and negative 3 on the right side. And we enclose the negative 3 with a parenthesis here because that's an open circle there, means that that negative 3 is not part of the set. And that's the way we show that in interval notation. Okay, so we've got the inequality, we've got the number line, we've got the interval notation. So I wanted to write all those things down. All right, so that problem illustrated some things we needed to talk about. The next thing that we need to talk about is we need to deal with compound inequalities. A compound inequality is simply one that has two order symbols in the same statement. So a typical example might look like this. Negative 6 less than or equal to negative 3x, excuse me, plus 3, which is less than or equal to 15, we'll say. All right, and actually let me change that slightly. Let me just make that second one just less than. So one of them is less than or equal to, the other one's less than. All right, so with a compound inequality like this, the idea is to just solve for x as the middle part of that inequality, is to get the x by itself as the middle part of that inequality. So the first thing we do is we go through and we subtract 3 from all three parts of this inequality. All right, so when we do that, we get negative 9 less than or equal to negative 3x, which is less than 12. And then what do? On our next step, we're going to go through and we are going to divide everything by negative 3, right? We're dividing each part of this inequality by negative 3. And so when we do that, we have to reverse the ordered direction, like so, right? Remember, when you divide by a negative or multiply by a negative, you got to reverse the order symbol's direction. So that gives me positive 3 greater than or equal to x, which is greater than -4. Right, now the only problem with this inequality, the way it's written, is notice that the bigger number, the larger number is on the left, and the smaller number is on the right. And with this type of compound inequality, you never write it that way. You always put the smaller number on the left and the bigger number on the right, just like you would on a number line, right? And so you need to rewrite this in the reverse order. So you start it with -4, and you just read it from from right to left in this case. Read it from right to left. So you have -4 less than x, which is less than or equal to 3, like that. It's almost like you were just taking a pair of scissors and cutting around, on a dotted line around this, and then flipping it the other direction is all you're doing. And this is the way you always want to write a compound statement like this particular problem. Now, on a number line, what this means is you're looking for all the numbers that satisfy both of those statements. And when I say both of those statements, this is simply shorthand. This statement right here is simply shorthand for these two statements, x greater than -4 and x less than or equal to 3. Because it's a shorthand for an and statement, what we're doing is we're looking for numbers that make both of those true. The numbers that are both greater than -4 and less than or equal to 3. And the numbers that do that are all the numbers between -4 and 3, right? So if that's -4 right there and that's 3 right there, right, we're looking at all the numbers between those two. Those are the only numbers on the number line that make both of those statements true, that they're both greater than -4 and less than 3 at the same time. And so we are shading everything between -4 and 3, like this. And for this kind of and statement, this type of inequality, you typically get a nice little interval like that. Now notice -4 is not part of the set, so we put an open circle on that one. And 3 is part of the set, so we put in a filled-in dot on that one. And so that would be the solution on a number line. And then when we put this in interval notation, we'd write a -4, comma 3. -4 would have a parenthesis, and 3 would have a bracket, like that. All right, so I wanted to remind you a little bit about compound inequalities also as we get into our main topic for the day today. Now, our main topic, are quadratic and rational inequalities, and quite frankly, it is more difficult. When you look at linear inequalities, except for the graphing stuff at the end, basically the algebra that you're doing is basically the same as when you solve a linear equation. But inequalities that are quadratic or rational are definitely not the same as quadratic equations or rational equations. So let's look at this a little bit, and let's move on to quadratic inequalities. So I want you to think about a quadratic equation like x squared minus 2x minus 3 equals 0. Very easy quadratic to solve, right? You just factor this expression. That's the easiest way to solve it, at least. Factors easily x minus 3 times x plus 1. Set each factor equal to 0. And you solve. And you get x equals 3 and x equals -1. And those are the solutions to this inequality. Just 3 and -1. There's two solutions to this equation, rather. Those are two solutions. Those are the only two numbers, only two real numbers that make that equation a true statement. Well, if we do the same thing, or look at the same problem but as an inequality, I want to show you the difference here and the step that makes this a really different situation. So you've got x squared minus 2x minus 3 greater than or equal to 0. And so you factor x minus 3 times x plus 1 greater than or equal to 0. And here is where it messes up a little bit compared to what we did with an equation. See, over in in the equation, when we're looking at this equation right here, we've got two numbers multiplied together to give 0. And the only way that two numbers can multiply to give 0 is one of them is 0, right? And so what do? We set each factor equal to 0 and see what x value makes each of those factors equal to 0. But with this inequality, what have we got here? We've got a multiplication problem. And let's not worry about the fact that it's equal to 0 also. Let's just look at the greater than part. You're saying that x minus 3 times x plus 1, that multiplication problem, that when you multiply those two things, you get a positive answer. And see, so what I frequently see on a test when a student who has not done any of the homework on this tackles a problem like this will be their next step. They'll say x minus 3 is greater than or equal to 0, or x plus 1 is greater than or equal to 0, and they'll proceed on with the problem like that. And that is totally wrong. And the reason why it's wrong is because what is that person telling me when they just go on to that next step? They're looking back at the equation. They're saying, hey, this is exactly the same thing as the exact same situation as the equation, but it's not, because there are two ways that you could get two numbers multiplied together to be positive as the answer, right? That the product is positive. You can take two positive numbers and multiply them together and get a positive, right? But there's another situation that the person who wrote this statement down wasn't taking into account, right? A positive times a positive is certainly a positive, but it's also true that a negative times a negative is a positive as well, right? And so this is wrong right here. When a student says this is the next step right here, that's incorrect, because there are two ways you can get a positive answer. And see, so what we need to do here is we need to kind of get a handle on those individual factors, x minus 3 and x plus 1, and we need to see where each one of them is positive and where each one of them is negative. For what x values are they positive, and for what x values are they negative? And then we can look at when do you get two positives and when do you get two negatives, right? Because we want the answer in this problem to be positive because it says greater than or equal to 0. If it said less than or equal to 0, we'd want the answer to be negative. All right, so we need to look at the signs of each factor. And so that's what I'm going to show you a way to do that. We need to analyze the signs of each factor. All right, and so this is the way we're going to do this, is we're going to first identify what I refer to as the critical numbers for the inequality you're dealing with. The critical numbers are simply the places where the two factors that you get are actually equal to 0. So you set each factor equal to 0, just like you would have for the equation, and you get the critical numbers -1 and 3. All right, and then on a number line, you go ahead and separate the real number line into pieces based on those critical numbers. So in other words, you mark -1 and 3 on the number line, like that. And then what you do is you choose test numbers in between those critical numbers, right? You choose test values in between the critical numbers. Now notice I put the critical numbers kind of heavy dark print there, and so the test numbers that I'm going to choose are going to be a little bit lighter and they're going to be in a different color. So all you're doing is picking numbers out of each of the intervals. So like you need a number that's less than -1. Anything less than -1 will be fine. So you could pick -983 if you wanted to. Now I'm not going to do that. I'm going to pick -2. Right, and then you want a test number between -1 and 3. And when I can pick 0, I pick 0. Right, because 0 always makes the arithmetic easy. And then I pick a test number greater than 3, like maybe I might pick 4. All right, so when I say test numbers, this is what you're going to do with these test numbers. You take the two factors that you're dealing with, in this case x minus 3 and x plus 1, and what we're going to do is we're going to analyze the signs of those factors based on the test numbers we've just picked. So like the first test number I've got is -2. What you do is you just substitute -2 into each of those factors for x. right? So you get negative 2 plus 1, which is a negative number. It's negative 1. And so I just put a negative sign there when I substitute that in like that to show that I got a negative answer. Put negative 2 in place of x minus 3, in place of the x in x minus 3. Negative 2 minus 3 is negative 5. And so I put a negative sign right there. Now what those negative signs are telling me is that not just at negative 2, but for any x value less than negative 1, those two factors are going to be negative, no matter what x value you pick. Anne-Marie, do you have a question?
I think I just sussed it out. I was wondering why you was using x negative 3 rather than the x equals 3, but we doing the equation, right? We're solving for x.
You're looking at the factors, right? And so,
Yeah.
I took x minus 3 equals 0, I set it equal to 0, and I get x equals positive 3, right?
Okay, yeah. Thanks.
Yep, and so then the factors, I'm using the exact factors that I had in the problem. So that's x minus 3 and x plus 1. All right, so now we go on to the next the next test value, which is 0. And you do exactly the same thing. You substitute 0 in place of x in each of the factors. So you have 0 minus 3 is negative 3. So that's a negative number. So I put a negative sign there. 0 plus 1, I put 0 into the other factor. That's a positive number. So I put a plus sign there. And so what's that saying? Those two signs are saying that for any x value between negative 1 and 3, x minus 3 will always yield you a negative answer, but x plus 1 will always yield you a positive answer. And then finally at check 4, I put 4 minus 3, and I put 4 in each factor. 4 minus 3 is positive, so I put a plus sign there. And 4 plus 1 is 5. That's positive. I put a plus sign there. So now I've got this nice little chart, and this little table that I've got here gives me a good picture of when each of the factors is positive and when each factor is negative. Now, what are we looking for? We don't care where each factor is positive or where each factor is negative. What we care about in our problem is we want to look at the product, x minus 3 times x plus 1, and we want to know where that's positive or where that's negative. And so what do you get? Less than negative 1, what do you have? Both factors are negative. And so when you multiply two negatives, you get a positive. And so I put a plus sign there. Between negative 1 and 3, one of the factors is positive and one of them is negative, and so the product would be negative. And then finally, greater than 3, both factors are always positive, and so I put a positive times a positive is a positive, and so I put a positive sign right there. All right, now what are we looking for in this problem? We are looking in particular, remember, our original problem has a greater than or equal to. We are looking for positives, right? Because it says greater than or equal to 0. And so down here at the end, we want to know where the product is positive. And the product is positive for everything less than negative 1. I'm going to shade those on the number line. And everything greater than 3, like this. And negative, because it says greater than or equal to, negative 1 and 3 are both part of the set. So I put solid dots right there. And that's a picture of the solution set to this inequality. And then in interval notation, you just simply write both of those sets out in interval notation. Notice this one has 2 pieces to it. And so you got to write both pieces in interval notation. So the first piece is everything less than or equal to negative 1. So that would be negative infinity to negative 1, bracket like that. And then the other piece is 3 to infinity. And then I put a bracket around the 3. And then I connect those. When you need 2 pieces like that, when you have 2 pieces on the number line and when you're using 2 pieces in interval notation, you have to connect them with a union symbol. And the union symbol is like this big kind of block U there that you're using. And that just says that you're taking those 2 sets and combining them and making them into one set, basically. And so we've got the solution to this inequality. The solution to this inequality are all the x values less than negative 1 and all the x values greater than 3. Less than or equal to negative 1 and greater than or equal to 3. any x value between -1 and 3, if you tried to check this inequality, it would make it a false statement, right? And so we have finished the problem. Now let me show you, let's continue with this problem for a minute. How we're doing it. We're doing great on time. So you have x squared minus 2x minus 3 greater than or equal to 0. On the number line, what did we see? We saw that it was everything less than -1, everything greater than 3, and equal to, I should say, on both of those. So this is our solution set, right? So these are solutions to this inequality, supposedly. So let's pick numbers out of each of those intervals, and let's actually check the inequality in each one of those, all three intervals, and let me show you what we're talking about. So let's just take some number, and I'm not going to pick the test numbers. I'm going to do something different here. So let's say I pick -10, right? -10 is over there less than -1. So let's check x equals -10. So when I check x equals -10, I go to my inequality, and every place I see an x, I put -10. And I put greater than or equal to 0, but I'm going to put a question mark here because we're trying to check to see if that's actually true. So I get 100 plus 20 minus 3 greater than or equal to 0. Well, that gives me 117. Well, 117 greater than or equal to 0, which is definitely true. And so what are we saying here? That -10 is clearly a solution to that inequality. All right, let's pick a number between -1 and 3. So let's do a different one. We'll do this in a different color. Let's say we pick 2. 2 is between -1 and 3, so let's check x equals 2. So you get 2 squared minus 2 times 2 minus 3 greater than or equal to 0. So that gives me 4 minus 4 minus 3 greater than or equal to 0. And that gives me -3 greater than or equal to 0. That is clearly false, right? And what are we saying? That makes sense because -2 is not shaded here. -2 should not have been a solution to this inequality, and it's not, right? We get a false statement when we try to put 2 in for x here. Then let's finally choose, 8. 8 is certainly greater than 3. So let's check it. X equals 8. Right, so that gives me 8 squared minus 2 times 8 minus 3 greater than or equal to 0. Again, that's a question mark there. Right? We're checking to see whether this is true or not. So you get 64 minus 16 minus 3 greater than or equal to 0. That gives you 45 when you do that arithmetic there, greater than or equal to 0, which is true. So 8 is definitely a solution, and it should have been because it was a number that was shaded. But that's what we're talking about doing, is we're trying to find all the numbers that make this inequality a true statement. Also, by the way, if we sketch the graph of the equation, if you look at the graph, y equals x squared minus 2x minus 3, right? Notice that x squared minus 2x minus 3 is the expression I had. If we actually graphed x squared minus 2x minus 3, let me show you that briefly here. So this will be the grapher I use during the semester. Sometimes I'll bring in a graphing calculator and actually show you some screenshots of a graphing calculator also. I will do that some during the semester, but when I want to do a decent graph here and show everybody, I'm actually going to use this app. And so let's see. Okay, so here's my graph. And what I want you to notice is where this graph crosses the x-axis and where it is above the x-axis and where it's below. See, it's above the x-axis wherever it's positive, and it's below the x-axis wherever it's negative. And notice, sure enough, where does it cross the x-axis? It crosses the x-axis at the two critical numbers we found in this problem, at -1 and 3. And notice that for everything left of -1, the graph is above the x-axis. That's where it's positive. Everything to the right of 3, it's above the x-axis. And that's where it's positive. And that's what we're actually finding here in this problem. And so this actually relates very closely to graphs as we go through and solve these inequalities. And so I'll look at these graphs occasionally and show you how this is connected to the graph. Okay, so what we just found then, excuse me, is that this graph crosses at -1 and 3. Right, and so what are we saying? That for all of the x values to this side of -1 and to this side of 3, the graph is above the x-axis, right? That's what we're looking at. It's above the x-axis when it's positive. It's below the x-axis when it's negative. Right, and I think that's a good thing to know going into these problems, is that that's really what we're doing. All right, so let's look at some more problems here. We really talked a lot about that problem. We're not going to spend quite as much time. We wanted to kind of illustrate the process, and so now we're going to kind of concentrate on the process as we go through this. So next problem, if 2x squared minus 5x minus 3 is less than 0. 2x squared minus 5x minus 3 is less than 0. All right, so this is an inequality, not an equation, right? So what are we going to do? We're going to find the critical numbers first. And so to find the critical numbers, we factor the expression. If it didn't factor, by the way, you would have to use the quadratic formula to find the critical numbers, or some other method to find the critical numbers. And that could definitely happen. I'm not going to give you problems where you have to use the quadratic formula, because I would rather you spend your time worrying about the process for solving these rather than finding the critical numbers and having some difficulty with that. So this polynomial factors 2x plus 1, x minus 3. And so the critical numbers, remember, you take each factor and set them equal to 0. And so the critical numbers would be at -1/2 and at +3. Those are my two critical numbers. All right, and what do we want to do? We want to put those critical numbers on the number line. By the way, you would be surprised how many times I see this on a test. Now, can you see, where the 3 is on the left and the -1/2 is on the right? Students not paying attention to what they're doing, and they get everything wrong on the number line. So make sure that when you get the critical numbers, you put them in order on the number line, in the correct order. So here's -1/2 and here's 3. All right, so we pick test numbers in between those values. And so the test numbers I might pick here are -1, possibly 0, and 4. And so what are we going to do with those test numbers? We're going to substitute those into our two factors, 2x plus 1 and x minus 3. All right, so we start doing that. We put -1 in for x, right? All you're doing is substituting -1 in for x for each of those factors. So -1 minus 3 is -4. That's a negative. And let me do this in a different color here. That's a negative. I'll put -1 in place of x for 2x plus 1. So 2 times -1 plus 1 is -2 plus 1, or negative. Put in 0. Substitute 0 for x in both of those factors. 2 times 0 plus 1 is a positive. 0 minus 3, though, is a negative number. That's -3, so that's a negative. And then put in 4 for x in each of the factors. 2 times 4 plus 1 is 9. That's a positive. 4 minus 3 is +1, so that's a positive. All right, but what are we looking at? Okay, that's fine. We've got the nice little analysis of the factors and their signs. So now let's look at the product of those two numbers. So we just go down the columns, and we're saying that less than -1/2, we're multiplying two negative numbers together, and so that gives me a positive. Between -1/2 and 3, we're multiplying a positive times a negative, so that gives me a negative. And then greater than 3, I'm multiplying two positives together, I get a positive. All right, so there's an analysis of the signs. What are we looking for in this problem? We are looking for, go to the inequality, we are looking for negatives. Not positives, but negatives, because it says less than 0. We want to know when that product is negative. And so that product is negative. Where is it negative? When one of the factors is positive and where one of them is negative, right? And that would simply be between negative 1/2 and 3. Here's my solution set in this case. It's everything between negative 1/2 and 3. And because it says strictly less than 0, we put open circles there around negative 1/2 and 3. And so in interval notation, our solution set, the solution set here in interval notation would be from everything from negative 1/2 to 3, not including negative 1/2 or 3. And so we put both of those in parentheses. All right, and so we've solved that inequality. Are we doing okay? Does anybody have any questions as we've gone through the first two examples? So anybody have anything that they want to ask about?
No.
I'm good.
Okay, very good. Okay, good. So now this next example will look a little bit different. It's not quadratic as it turns out, but it's the same kind of problem. Let's say we have x plus 2 times 3x minus 1 times x minus 5 is greater than or equal to 0. So now notice this expression, this polynomial inequality, is already factored, first of all. So I don't have to worry about the factoring. It's got 3 factors, so it's not quadratic, but it's the exact same process. The only difference here is that instead of having 2 critical numbers in this problem, since there's 3 factors, I'm going to have 3 critical numbers. Everything else is exactly the same. So critical numbers in this problem. X plus 2 is equal to 0. And so that would give me x equals negative 2. 3x minus 1 is equal to 0 would give me x equals 1/3, right? Add 1 and divide by 3. And then x minus 5 is equal to 0 would give me x equals 5. So this one has 3 critical numbers. So the little chart that we're completing, this table, is just going to be more extensive in this problem. Excuse me. So we have negative 2, 1/3, and 5 is my critical numbers. And it, we're just kind of ballparking things, so don't worry about it being to scale necessarily. I'm not going to make a big deal about that on this. This number line is simply a visual to kind of get us organized on the information we're setting up here. All right, and so so by the way, if you can hang on with me, and I know some of you may have to leave possibly, but if you can hang on through the end, it would be great on this one, because the problems we're going to do, there's some unexpected things that happen when we get to rational inequalities that you're not going to be ready for if you don't see the whole thing. So hopefully you can stay, for those of you who are live with me, hopefully you can hang on and stay till the end. If you can't, I understand, definitely. All right, so we pick test values. So you have negative 3, and now notice I need 4 test values. I could pick 0. I could pick 1. Anything between 1/3 and 5 would be fine. And I could pick 6. Those are going to be my test values here. And then what are you doing here? You're taking those numbers and you're substituting them in place of x in each of the factors. So let's use negative 3 first. I'm substituting negative 3 into each of those factors. So negative 3 plus 2 is a negative number. Negative 3 times negative 3 minus 1 is negative 10. It's a negative number. And negative 3 minus 5 is negative 8. It's a negative number. So all 3 factors are negative. I substitute 0. 0 plus 2 is a positive. 3 times 0 minus 1 is a negative. And 0 minus 5 is a negative. Substitute 1. 1 plus 2 is a positive. 3 times 1 minus 1 is a positive. And then 1 minus 5 is a negative. And then substitute 6. 6 plus 2 is a positive. 3 times 6 minus 1 is a positive, and 6 minus 5 is a positive, like that. And so that's a nice little picture of the signs of each of the individual factors. And then we look at the multiplication problem. So you have x plus 2 times 3x minus 1 times x minus 5. But now notice you got three numbers you're multiplying together. So like less than negative 2, what are you doing? You're taking a negative times a negative times a negative. And a negative times a negative is a positive, but then a positive times a negative is a negative, right? When you multiply three negatives together, you get a negative answer. Between negative 2 and 3, you're taking a positive number and multiplying it by two negative numbers, and that product is positive. Between 1/3 and 5, you're picking two positives and a negative. You're using two positives and a negative. When you multiply those together, your answer would be negative. And then greater than 5, you're multiplying three positive numbers together, you get a positive. And so you get that, that little picture of the signs here. Now, what are we looking for in this problem? We are looking for positives, because that says greater than or equal to 0. And so down below, we are looking for where the product is positive. And the product is positive between negative 2 and 3 in this interval here, and greater than 5, this interval over here. And all of the critical numbers are included in this set because it's greater than or equal to. Right? And so that's a picture of the solution set to this inequality. And then in interval notation, the solution set is going to be negative 2 to 1/3, enclosing both of those in brackets, and then union, and then bracket 5 to infinity, like that. And by the way, if you looked at the graph of this function, or this equation, if you looked at the graph, what you would end up with is, I'm going to kind of squeeze it in here at the bottom here, is that the graph is, like if this is negative 2 right here, and here's 1/3, and here's 5, that the graph actually crosses above the x-axis between negative 2 and 1/3, is below again, and then comes back up here and crosses above at 5 again. That it's above, notice it's above the x-axis, that's where it's positive, between negative 2 and 1/3 right here, and then greater than 5 over here. And that's what we're finding graphically in the problem. Don't worry about the graph at all. I just want you to start thinking about the graphs and connecting it, but that's not going to come up for us until later in the semester, so don't panic on the graph part of it at all. Okay, it's certainly not something I'm going to ask you to be looking at in these problems at this point. All right, so I think we are doing okay, and hopefully no questions about that problem. I think we're okay. Sounds like we are. So the next one I want to look at, just a couple of other examples with quadratic inequalities, and then we look at a rational inequality to finish the day with. So the next example I want to look at, let's look at x squared minus 6x plus 9 is less than 0. X squared minus 6x plus 9 is less than 0. Now, when you factor x squared minus 6x plus 9, this factors x minus 3 times x minus 3. Or, if you wanted it as x minus 3 squared, that's fine. Now, as far as the critical numbers, notice there's just one critical number. So now you could proceed on with this problem just like we were doing before. It's the same factor, so you get the same critical number. So there's just one critical number, and that's 3. So you could just proceed on just thinking about the problem that way. So there's 3. And notice you only need 2 test numbers. You only need a test number to the left of 3 and to the right of 3. And the only factor you're really checking is x minus 3. You've got x minus 3 sitting over here. If you wanted to, you could even write it down twice since it's a factor twice. Or you could write x minus 3 squared. Any one of those would work. So when you put 0 in for x minus 3, you get a negative. So both of those are negative. When you put 4 in for x and x minus 3, these are both positive. But what happens when you take x minus 3 times x minus 3? Well, 2 negatives give you a positive, and 2 positives give you a positive. So notice this expression is always positive, and you could have told that at this step right here. Because what do you have? You have x minus 3 squared, and when you square a number, you always get a positive. Square a real number, you always get a positive answer. But what are we looking for in this problem? We are looking for negatives. And there aren't any, right? There are no negatives down there. And so this multiplication problem is never negative. It's always positive, or 0. When x is equal to 3, it's actually equal to 0. And so there's no solution to this system, or this inequality. Right? There are no x values that make it true. And so you have to be aware of the fact that that can happen. So you have to watch for that. So that's definitely something I wanted to point out here. And then let's see. One last example with quadratic inequalities before we move into rational inequalities that I want to talk about. Let's say we have 16 minus 25x squared is, let's say, less than or equal to 0. 16 minus 25x squared is less than or equal to 0. Now, 16 minus 25x squared is the difference of two squares, and if you leave it like it is, which is fine, the x squared is not the first term here, but you could factor it like it is if you wanted to. There's no problem doing that, in which case this factors 4 plus 5x times 4 minus 5x. Remember, that's the difference of two squares. A squared minus b squared factors a plus b times a minus b. Since the 16 is first, and it's the first term written, then the 4 has to be the first term written in both of those binomial factors there. And so the critical numbers in this case, when 4 plus 5x is equal to 0, you get x equals negative 4/5. And when 4 minus 5x is equal to 0, you get x equals positive 4/5. So this all looks pretty routine. You just have to be careful in one place when you're filling out this chart. You know, I put negative 4/5 here and positive 4/5 here. The test numbers that you pick, maybe negative 1, 0, and 1. Those would be fine. And the factors I'm checking are 4 plus 5x and 4 minus 5x. So you're putting negative 1 in for x in each of those, and you have to be careful about the way this works out. 4 plus 5 times negative 1 is 4 plus negative 5. That's negative. But be careful, 4 minus 5x, when you put negative 1 in place of x, that's 4 minus, let me write that out. That's 4 minus 5 times negative 1. And so that's 4 plus 5, or 9. And so that factor is positive right there. So that you might not have expected that to happen. You put 0 in place of x for both of those factors, and notice 5 times 0 in both cases is 0. And so you're going to end up with a positive for both of those. And then when you substitute 1 in for x, you're going to get a positive number and a negative number. So the signs don't look like maybe some of the other ones did, possibly. And so you end up with a negative when you multiply the factors together, a positive and a negative. And what are we looking for in this problem? We're looking for negatives, right? Looking for negatives here. And so the negatives occur when you have an x value less than negative 4/5, and negative 4/5 would be included, and greater than positive 4/5. And 4/5 would be included also. And so the solution set in this problem is negative infinity to negative 4/5, bracket, and then 4/5 to infinity. Might have been, the signs might not have looked like you thought they were going to work based on the first groups of problems we looked at. that we looked at there. All right, so we've worked our way through some good quadratic inequalities, lots of examples there. And so then we want to turn our attention to rational inequalities. Now, a rational inequality remember, when you see the word rational, you're talking about a fraction. And so let's talk about a rational equation first of all. So a rational equation, a simple rational equation might look like this. X plus 6 over x minus 5 is equal to 0. Right? That's an example of a very simple rational equation. And actually, the way you would solve that rational equation, it's actually a really simple rational equation to solve, is you'd simply just multiply both sides by x minus 5 to clear the fraction. X minus 5 would go away there. And you just left with x plus 6 equals 0, because 0 times x minus 5 is still 0. Super easy to solve, and you end up with negative 6. You just clear the fractions out by multiplying both sides by the denominator there, and then you can solve what you've got left there, which is a pretty simple equation. The inequality, unfortunately, you cannot do that. And the reason why you are not allowed to do that, why that's a no-no for this kind of problem. So let's say we have x plus 6 over x minus 5 is greater than or equal to 0, right? So now it's an inequality. This is a problem. When you multiply both sides by x minus 5, like that, that's an issue, right? And the reason why is, remember, way back when we were talking about this at the beginning of class today, let me flip all the way back here, and it's been a while since we've talked about this today, but remember, when we talked about inequalities, when you're multiplying or dividing both sides by a negative, you have to flip the order symbol, right? So in this problem, we did that right here, where we flipped the order symbol because we were dividing by a negative number. When you multiply or divide by a negative number, you have to flip the order symbol. And the problem here is I'm multiplying both sides by x minus 5. What am I doing? Am I multiplying by a positive or a negative? And for those of you who are listening right now, what are you multiplying by, a positive or a negative there? I'm multiplying both sides by x minus 5. Am I multiplying both sides by a positive or a negative?
Positive.
No.
It's a negative.
No. All of you are wrong. And I knew that that's what would happen, because that's your answer, right? It's going to either be positive or negative. And why are you all wrong on this? And the reason why you're wrong is it's got a variable in it. You don't know whether it's positive or negative, right? It could be positive, it could be negative. It depends on what the x value is. And so you don't know whether you're multiplying by a positive or a negative here because it's a variable, right? Multiplying or dividing by a constant, you know it's either positive or negative because it's a constant. In this case, you're multiplying by a negative. And because you're multiplying by a negative, multiplying by a variable, you have no clue whether it's a positive or a negative. Right? Multiplying by a variable, we don't know if this x minus 5 is positive or negative. Sometimes it's positive and sometimes it's negative. It depends on the x value that you're talking about. So that's a problem. You can't do that, in other words. You're not allowed to just multiply both sides by a factor like that in an inequality because you don't know whether to reverse the order symbol or not. Now, there are some kind of convoluted ways you can try to get around that by dividing the problem up into cases, but we don't have to do any of that. We can just treat this like we do a quadratic inequality and just identify the critical numbers. The only difference between this problem and this problem is that one of them is a multiplication problem and one of them is a division problem. The factors are both the same, and the rules for multiplication and division are the same as far as positives and negatives, right? And so there's really not a lot of difference in how you solve this inequality, except for one huge difference that we'll see in the problem. So, moral to the story, are you allowed on a rational inequality, are you allowed to multiply both sides by a variable quantity like that? No, you can't just clear the fractions, right? You're not allowed to do that. And you're going to get the problem wrong if you do that. I promise you're going to get the problem wrong because you're going to end up with something that's no longer a true statement. And so what we've got to do is kind of analyze the signs like we've been doing. So the critical numbers in this problem, just find the critical numbers just like you would any of the other problems. You have x equals -6, and you have x equals 5. By the way, one thing I'm really happy about is a few minutes ago I asked you guys to answer, am I multiplying by a positive or a negative? And I got a lot of you responding. Most of you were responding. Now, all of you were wrong. I understand that. Don't worry about that. But all of you were responding. That was the good thing there. I'm glad. That means that you were all still kind of listening to what was going on. In a face-to-face class, I can see everybody, and I know when people have kind of drifted away or something like that. In this case, because I can't see any of you, I don't know whether you've drifted away from me or not. In my calculus class the other night, I asked questions towards the end especially, and there's no responses from anybody. And so I was pretty sure that a lot of people had either left the room or had fallen asleep or both. And so I'm really happy that you guys are still with me. So that's good. All right, so we analyze the signs of these factors around these critical numbers. So this is all looking exactly the same as what we've been doing. So you should be, I think, getting comfortable with this process. When I first worked through the first one, I know you probably were unsure as to what I was doing, but as we proceeded on through more and more problems, it probably started becoming a little bit more clear how I was getting all the signs and everything. That's typically the case here. All right, so I'm looking at x plus 6 and x minus 5, and I substitute -7 in here, and I get a negative and a negative, right? When I substitute -7 for x. When I put 0 for x, I get a positive and a negative. And when I put 6 for x, I get a positive and a positive. Now I'm dividing. I'm not multiplying anymore, I'm dividing, but the rules are still the same. So dividing two negatives gives me a positive. Dividing a positive by a negative gives me a negative. And dividing two positives gives me a positive. Now, what are we looking for in this problem? Are we looking for positives or negatives? Somebody tell me, are we looking for positives or negatives in this problem?
Negatives. Positive.
Now, I gave you a hint. I circled the order symbol there, right? What does it say? Greater than or equal to 0, right? That's the inequality we're looking for. Yeah, so that's right. Some of you are saying it. Positives, right? When it's greater than or equal to 0, we're looking for positives, right? If it was less than or equal to 0, I'd be looking for negatives. So I'm looking for positives, and so where do those occur? Less than -6 and greater than 5. Like that. Now, and you guys answer this question for me. Do I include, this says greater than or equal to. Do I include the -6 and the 5? Do I not include them? What's going on there?
Yes, include it. Yes.
And see, I asked this question. I set you guys up on purpose. You're wrong in that I get this. I include -6, but I don't include 5. There's a reason why 5 does not get included in this set at the end, and that the solution set is -infinity to -6 with a bracket around the -6, but the 5 has a parenthesis. Why? What's the difference between the 5 and the -6? It does say greater than or equal to 0.
Is it because that's where the variable was?
No. It's a good try, but that's not why. Why does the 5 not get included, but the -6 does? It does have an equal sign there, so with quadratic inequalities, I would have included both of them. Like if I had solved this quadratic inequality, I would have gotten -infinity to -6 bracket, and then union, and then bracket 5 to infinity. That one would have had brackets on both of them. But this rational inequality, there's a problem with the 5. Does anybody know? where did the 5 come from? Which factor? X plus 6 or x minus 5? Which one did it come from? It came from the x minus 5. That's right. I heard Cynthia say it, I think. Where is the x minus 5? Is it in the top or the bottom?
The denominator.
It's in the denominator. So when you try to check 5, where are you going to get, what's going to happen with the 5 there? It's going to give you a 0 in the denominator, right? If you check x equals 5 in the original inequality, you get 5 plus 6 over 5 minus 5. That gives you 11 over 0. That's a problem. 11, you can't divide 11 by 0. That's an undefined expression. That's a meaningless expression. That doesn't work. When you check x equals negative 6, you get negative 6 plus 6 over negative 6 minus 5. You get 0 over negative 11. Yeah, that's okay. You can divide 0 by something and other than 0, and you just get 0. See, so getting 0 in a numerator is okay, but getting a 0 in the denominator is a problem. And so even though it's
always going to be like that?
Yes, for rational inequalities, that's right. And so you always have to throw out anything that makes the denominator equal to 0. So that's a big difference between rational inequalities and quadratic inequalities. Let me show you. Let's work through another problem here. Let me show you another situation where that happens. So let's say I have x plus 2 over x minus 3 times x plus 4, less than or equal to 0. All right, so what are the critical numbers here? Right, you've got 3 factors, right? You said each of those equal to 0. And this should be pretty straightforward, right? You get negative 2, 3, and negative 4, right? Those are my critical numbers. And so I go to the number line, and I put negative 4 here, and negative 2, and then 3. Now, before we do anything else, what you could do is you could think about those critical numbers and about whether they get included in the set or not get included. And you could take care of that here rather than waiting until the end. That way you don't forget. So this says less than or equal to 0, right? There's an equal to there. And so that means typically we would include the endpoints, but in this case, we don't include all of them. We only include the ones that give us 0 in the numerator. So negative 2 works because negative 2 comes from x plus 2, and that's in the numerator. But negative 4 and 3 are both critical numbers from the denominator, and so those have to be thrown out no matter what. Right, so the ones from the numerator include, if it says less than or equal to 0 or greater than or equal to 0, you include critical numbers whoops, be nice if I read it right. From the numerator, but you exclude, so you include critical numbers from the numerator, exclude critical numbers from the denominator, right, automatically. So since x minus 3 and x plus 4 are both in the denominator, negative 4 and 3 have to be thrown out. That does not happen with quadratic inequalities because quadratic inequalities are all multiplication. There's no division. You never have to worry about that with quadratic inequalities. Rational inequalities, you have to worry about that. All right, so that's, I mentioned earlier that something was going to happen towards the end of class that was going to throw people for a loop if they weren't here to listen to it or they didn't listen to it on the recorded version. This is what I'm talking about. So this is what you got to be worried about with rational inequalities. Now, the rest of this, I'm just going to go through kind of in the interest of time and just fill out the signs. I think all of you are probably getting the hang of how these signs work out. And so you can go through and verify this on your own, but that's the way the chart's going to look in this particular problem as far as the signs go. So please go through that and make sure that you can reproduce that on your own, that you know how to deal with those signs. And so with the multiplication and the division, you end up with 3 negatives gives you a negative, 2 negatives and a positive give you a positive, 2 positives and a negative would give you a negative, and then 3 positives would give you a positive.
I thought three negatives gave you a positive.
Now think about it now. So, and if you get confused on that, just take 3 negatives and multiply them together. So what's negative 2 times negative 3, Anne-Marie?
Positive 6.
And then what's positive 6 times negative 6?
I thought it was negative 36.
Yeah, so 3 negatives gives you a negative.
Oh, what did I say? Positive?
Yeah, you did.
I'm losing it. Sorry. Forget it.
It's easy. All the signs start running together at the end. I understand that. So, all right. So go through and see if you can reproduce that. Here I'm looking at negatives because it says less than or equal to 0. And so negatives would occur less than negative 4 and between negative 2 and 3, like this. And so the solution set in this problem would be negative infinity to negative 4, parenthesis, and then union, and then bracket negative 2 to 3, like that. All right. Okay, so homework. Now the homework, no WebAssign homework on this material. It is, but instead I've got problems for you, and I'm going to include those in these notes, and I'm also going to send this out as a separate document. So these are the practice problems for solving inequalities. And so notice I've got 8 quadratic inequalities there, or polynomial inequalities, and then 5 rational inequalities. And so I will, they're going to be part of these notes. And they're also, I'm going to send this out, this document out separately probably, or post it on my Google site, or I'll send it through Remind. Somehow I'll make sure that everybody gets it. And so I definitely want you to be practicing this material. These are definitely problems that you can use as a practice for the exam. In fact, on the review, when we get to this material on the exam review, it's just going to say, see the practice problem set for solving inequalities. It's going to say, see these 13 problems. I will post the solutions to these eventually, or I'll send them out probably maybe early next week. I want to give you some time before I actually post the solutions. So it may be the weekend before I get that done. But I definitely want you to be working on these problems. This is good practice for this material. So, all right, does anybody have any questions about any of that? Cynthia, do you have a question?
No, I was going to ask if it was on the test, but I see you said
yeah,
it is going to be.
Definitely. Hey, and that is a, when you ask that question, for all of you, for those of you with me live or recorded, whatever, you never have to ask me that question. When we're covering material in class, you never have to ask me, is this going to be on the exam? Because the answer will always be yes. If we cover it during lecture, you're going to be tested over it somewhere along the line. It would be very rare that I cover anything in class that I'm not going to test you over. That would be very rare. So, and those who are with me in intermediate algebra, in this case right now live, I've got Anne-Marie and Charlotte, who are both in my intermediate class last semester. They can definitely tell you that if I covered it, it's going to be on the test, so somewhere. And if it's on the review, it's going to be on the test.
Yeah.
Yeah, right?
I agree.
Yep, okay. All right, does anybody have any other questions?
When should we expect this to go up? When should we check back, like today?
Well, it'll be part of the notes. You can always check it in the notes, but I'm gonna post this morning. I'll send it out to everybody this morning. So you should get a copy of this morning sometime. So. Okay. All right, then everybody have a wonderful day. Have a great weekend, and work on some algebra. Definitely keep up with the algebra homework, and we will be proceeding on into talking about functions and graphing starting when we come back on Monday. So it'll be a big switch as we leave equations and inequalities behind completely and move on to functions and graphing next Monday. So something to look forward to. Have a wonderful day, everybody.
Hey, have a good one.
Thank you.